All right. Hey, we're going to take a look at inductance in this video. Take a look here. We say, hey, this is, of course, Faraday's law of electromagnetic induction. We talked about how what happens is if I change the magnetic flux going through some closed path of conductor, that will create an electric field in the conductor that goes around in a closed path in a loop through the conductor. That E field, if I go and do an E field dot with a path, right, that actually will give me a voltage. Okay, we call this the induced EMF, or the EMF that we've caused to happen in that wire or in that conductor because of that changing flux through that path. There's some interesting applications of this. The fact that that path doesn't have to be in a wire. I could have just like a big metal plate, right? This solid metal plate. And if I have a closed path, I draw a path through that metal plate. There'll be electrical current flowing around. There'll be this voltage that creates that if I have changing flux through that plate. So, for example, if I had a coin, all right, hey look, there's a, look, it's George Washington on the coin. No, it's more like Ben Franklin. Hey, he's not on any coins. Anyway, point is, if I have this coin, right, imagine what would happen if I made a ramp, okay, and I roll this coin down the ramp. As it rolls down the ramp, it passes through a region where I have some magnets set up, so I have a magnetic field here. Well, as that coin enters that magnetic field, I could go ahead and I could choose a path going around that field, right? In that field, right? I could choose a path. And as it enters, the coin enters, I'll be increasing the flux in through that path. And if I have a change in flux, then I'll have a voltage and an E field created in that metal, right? It'll make electrical current flow around and swirl around in that metal coin, right? You say, now wait a minute. When this happens, right, I know that that flux, that current that I make in the coin, right, which in this case, here, let's just think about it. As it's entering the field, so I should have drawn this over here. Let's talk about as the coin is entering. I've done my path through there, right? You see I'm increasing flux in, so current has to flow around in that metal to make more flux go out of the page. So the current's got to flow around this way, right? So I'll make a little current that'll swirl around and induce current in that metal, right? And you say, well, as it's leaving, a little later on, as it's leaving that field, right, then I'll be decreasing flux in. And so current has to flow to try to make more flux go out. Sorry, to make more flux go in. Sorry, to cancel the change. Less flux in, so current has to flow to make more flux go in. Well, that would be current going this way. So the current will then switch directions and go the other way, my induced current in that coin. The point being that when I do this, you say, well, gosh, to do that to the coin, to give it energy, right, to flow the charges around, yeah? You say the energy's got to come from somewhere. You know what will happen? It'll slow down that coin, actually, as it goes through. Now, if I had different coins, like nickels and quarters and dimes and stuff, right, they'll be made out of different materials. And they'll have different dimensions and stuff to them, different sizes. And so what that means is they'll have different resistances. When I create this voltage, you know Ohm's law, delta V is IR? Well, my induced EMF is IR. But the different coins have different resistances, which means they'll make different currents, which means they'll make different strength magnetic fields, different amounts of current that will fight against the motion and slow it down different amounts. So different kind of coins will get slowed down by different amounts as they go down this ramp. Okay, I could have a series of these or something if I needed to. I could also put in, maybe I put in as it rolls along, it rubs up against some sensors, right? And the sensors, these are like hooked in, let's say this completes a circuit, and so it tries to run a little current through the coin like this, right? This might not be near this magnetic field, but later on or earlier. And I can see if I know the voltage that I set up there, right? And I can measure then how much current flows from this plate into this plate with a little ammeter, right? Then the point is, it's flowing through here. The point is, I can figure out what the resistance is of that coin. Okay, and so I'll know the R value, right, from that. And for this, the point is, with this, I can figure out what kind of coin people have put into this machine. What is this device I just described? It's the device that lets vending machines know what kind of coins you've put in. Have you ever wondered that, vending machines? How do they know whether you've put the correct change in? This is how they do it. Cool application of inductance, or inductors, or I should just say electromagnetic induction. Okay, getting back to where I was. So what I want to point out about this just real quick before I get on with today's lesson is anytime I change the flux through this closed path of conductor, and again it could be in a solid plate of metal, it could be in a wire that's in a loop or whatever. Point is, anything that changes that flux will make a voltage to fight against the change. Again, Lenz's law says that induced tries to fight against the change. So the point is, how do I actually do the calculation here? Okay, and of course we've got different problems in the packet where we're going through and doing this, but it's going to be d dt of that flux. Remember how you calculate magnetic flux? You say you got flux, that's the integral of B dot dA. Remember B field strength, that's how many field lines you have per area, how densely, tightly packed the field lines are. That's just flux per area. Flux per area times area gives you flux, right? Okay, so this is the way you would do it. If this B happens to be uniform over that area, then the B can pop out of the integral, right, can factor out, and if that angle's nice and constant, then the dot goes away, and so on and so on, right? You know, so basically that's going to have a cosine theta there, and if that angle is, right, if that angle is constant, then the B and the cosine theta will come out, and then just have the integral, the dA, that's just all the area. This will just be B times A times the cosine angle between them, if those things are nice and constant. Okay, if I don't have a changing B strength over the area. If I do have an area where the B field is changing, I'm going to have to slice it up in a bunch of little slices and do the integral, right? And add up the flux through each little bit of area. But anyway, but in this case, this is what we get. So this is what I'm going to put in for flux here. So it'll be the ddt of BA cosine theta. So I can generate this EMF if I'm changing the magnetic field strength, if I'm changing the area of the path, okay, that I'm measuring through, or if I'm changing the angle between the B field lines and that area vector, okay. So the area the field lines are making with that area. So you say, so all those, so any of those changing, I'm going to generate a voltage. Okay, what I want to say about this, I don't want to do much more with this at the moment, except to say that your text, Fletcher does a fantastic job of talking through how to work with this in the text, actually. Okay, and I'm actually really happy with Fletcher's presentation of it. Here we go. And so this is in chapter 19, Faraday's Law, section B here, Faraday's Law, in the chapter titled Faraday's Law. Okay, but here he kind of talks about this, what you can do to make that voltage. But then here, he runs through an example of plugging in BA cosine theta for your flux, and then talking through what will happen to the equation if different variables are changing and the others are constant. And then he runs through a crazy example where all three, B and A and theta, are all changing. And talks through a crazy example of how you would do that. And again, on the AP exam, they're not going to do a problem where all three are changing at the same time. That would be, they would start getting into the range where they're testing your math ability instead of your physics ability. And it would take a long time to calculate for one problem. But the point is, this example is really nice, okay, for thinking through what's going on. Okay, again, he then goes on, he talks about Lenz's law, but we do a better job of Lenz's law in class than you can with reading this. Okay, but that takes us to our last topic. Let me talk through, so I'm going to back up a step now. I'm going to talk about this induced voltage, this EMF is negative d phi b dt. I'm just copying down that line for my own secret reasons. Okay. Now what I'm going to do is, you know what? I'm going to come back to this. I'm going to draw a little picture of a circuit. Okay, and then we'll come right back to this. Let's say that I have a circuit. Look, simple circuit, simple. Look, I've got a battery, long lines, short lines. That's the high V side and the low V side, right? Right, that's my battery. Okay, and has some voltage, EMF. And I hook it up, and look, there's a resistor, sure, because every circuit has some resistance. The wires have some resistance to them. when I bring it down, I'm going to put a switch in so I can turn the circuit on and off. Now, you could tell me what would happen when I close this switch, click, and turn the circuit on. You're like, well, sure. My current, my hypothetical positives, would go from the high V side down to the low V side. As they go through here, they would lose potential energy as they go through the resistor. That resistance, they dump off energy, turn into heat at the resistor, and then they return to the low V side. And then just flown around, right? However, here's the thing. If I close this switch, then that'll make current flow through the wire, charges flowing. You see, now if charges are flowing, they'll make a magnetic field, won't they? In this case, which way is the field going? Well, they're going like in a loop. Which way is the field in the middle? Because that's where it's really strong, right? The fields all overlap. And again, if I do that first right-hand rule I showed you for current carrying wire, you grab the wire, thumb the direction of the current, right? Again, my current, if I close that switch, the current is going to start flowing this way. You say, well, gosh, grab the wire, thumb the direction of the current, fingers would curl around like this. So we're going into the page here, and that's going to happen all the way around. Or using that new third right-hand rule just for loops of current. You say fingers are the current, thumb is the field down the middle. So it's going into the board. I will make magnetic flux going into the page, right, in the center here. You say, but wait a minute. Before I closed that switch, there was no magnetic field. Now I close the switch, now there'll be a magnetic field. You say, wait a minute, that means here I have a closed path of conductor, and when I close the switch, I have a changing magnetic flux going through that closed path. Changing flux, that's going to make an E field, right? Which way is that going to go? It's going to make a voltage in this wire that fights against the change. The change happens because the current's starting to flow this way. It's going to make a voltage that fights against it. Do you see that? So when I close the switch, it actually creates a voltage in the wire fighting against the voltage of the battery. Okay? Now, here's the thing. For most circuits, when you turn this on, the amount of current going through this, it's going through this one loop of wire. It's not making a very big B field, right? There's not very much flux increasing in through the circuit. So this isn't a big deal, okay? But the ability of this circuit to make a magnetic field like that, how much field we get for every little bit of current that we have flowing, right? You say that thing's called inductance, okay? So we talk about so every circuit has some resistance, every circuit has some inductance, okay? Inductance, I'm going to use this symbol, capital L, for it. And you say, yeah, we've used L before, that was for angular momentum. We are not going to do a problem where we have inductance and angular momentum going on at the same time, so we'll be okay. Alrighty. But what this is, let me show you. So, like I said, for this circuit, this is not going to be a big deal, right? It's not very much flux getting made, so it doesn't make a very big EMF to fight against this. It's not really going to be noticeable. But what if this circuit wasn't just one loop of wire like that? What if the circuit was really loopy, right? In fact, I sometimes talk about inductance as being like the loopiness of the circuit. What if this circuit had something where the current had to spiral around a whole bunch, like a solenoid? Maybe there's a little electromagnet built into this, right? And the current comes in and it has to go loop, loop, loop around in that electromagnet. That's an area that's really loopy. That's a part of the circuit that has a lot of inductance. It's going to make a lot of magnetic flux for every little bit of current that flows through it. Okay? That's what this is going to be. Inductance is going to be how much flux we make for every bit of current flowing through. So check this out. d phi b dt, I'm going to rewrite that as d phi b di times di dt. This is just like a chain rule thing, right? Yeah? d flux dt is d flux di times di dt. Yeah? Okay. This thing is how much flux I get for how much current I have. It's that flux to current ratio. Look at this, I get this little bit more flux when I have a little bit more current, right? It's just it's going to be a direct relationship. And so we can just write that as, it's just the flux to current ratio, okay, is what this is, okay? And so flux to current, you say, hey, that's what we're going to call L. So this equation, my induced EMF, is negative L di dt. Do you see that? So this isn't flux anymore, this is current. And so the point is, what's the point in using this L guy? A couple things are going to come out of it. One thing is, I'm writing my voltage that I induce, my induced EMF, in terms of something I can measure with an ammeter, the current, and how the current is changing. Instead of having to talk about these hypothetical magnetic field lines that I can't see with my eyes or measure directly, right? Instead, now I'm doing it in terms of something I can measure on an ammeter. I put an ammeter in the circuit, right? And I measure the current that's flowing through here, yeah? And so I can tell you how quickly that current's changing. See, there you go, right? Okay, so this L guy, it's useful, okay? To show you something else important about this L guy. So this L guy inductance, what is it? It's really just the flux per amp, right? Now here's an interesting thing. Did I ever tell you what the units were for magnetic flux? That's the number of field lines, right? Well, it actually has a unit. The unit for flux is called, believe it or not, the Weber. And it's abbreviated WB, okay? Like that, okay, Webers. So you say inductance, that's just my flux per amp, per current, right? And so you say, oh, so that should be in units of Webers per amp. But again, Webers is a weird unit because you can't directly measure flux, right? So how often are you really going to be working with Webers? And so instead, what people oftentimes will use for inductance is they'll take this equation and they'll rearrange it. So let's see L, let's put the di dt under here. So EMF over di dt, this is just for figuring out the units, okay? EMF over di dt. You see, hey, that's just volts over, and then what's this? Amps per second. So divided by a fraction, right? So that'll be in units of volts seconds per amp. That's a V, that's volts. Okay, I'm not putting serifs on it because it's it's a unit abbreviation, not the variable. Anyway, so volts seconds per amp is actually the unit you usually see inductance in. Okay. Volts seconds per amp. Okay, that's the units. All right, for inductance. Okay, now, there's one more thing I want to show you about inductance, okay, before we start talking about like what it actually does in the circuit. One more thing about inductance, and that is, we can calculate then. This is really just the ratio of how many field lines we get going through our loop for every amp of current that we run through it, through that circuit, right, or through that device, yeah? That's our L value. I'm going to label that right on the diagram. I might label, oh, this thing has an inductance L. All right, so the point is, can we write the equation for the L for a solenoid? This derivation is in your unit packet. I put it in there for you, but I just want to show you one quick thing about it, so I'm going to derive it real super quick, okay? So L is just the flux per amp, right? Flux per current. So let's do an example real quick. For a solenoid. Okay? Its inductance is going to be its flux per current, right? Now flux, you say, I remember what flux is. It's BA cosine theta, right? Okay? Now, if I have a solenoid, right, that's again just this helical winding of wire, right? I've got these field lines shooting through it, right? You'll say, hey, that's just going to be, again, the area vector, area is going to be right across. The area vector is going to go nice and it's normal to the surface of the coil, right? So it's sticking straight that way. It's in the same direction as the B field. And so the area vector is just normal to the coil face, right? So just going like this, and the B field line is going like this. You see, hey, those are going to be parallel to each other. Cosine of 0 is 1. So it's just going to be B times A. All right? Now, that's the flux going through one loop, right? If I put in the B field strength at the heart of a solenoid, we derived that before. for a solenoid that was mu naught Ni. You say, wait, what's that lowercase n? That's the loops per length, how densely packed the loops are in my solenoid, right? So I could rewrite that as mu naught n loops per length times I, right? Now that's just the field strength at the center. But what I want is the flux. But I have that same number of field lines going through not just one loop, but every time that solenoid goes around, I'm getting more and more flux going through the circuit, through the path. And so I actually am going to have to say n times the flux of one loop, if I've got n loops. So this is actually going to be, the flux I have going through is actually going to be n times BA, and B, the field strength is this goes in there. So I'm going to have n versus B, I've got mu naught n over L times I, and then I have the area of my solenoid, right? That cross-sectional area of my coil, right? And so you say, hey, n times n, and say, oh, wait, and be able to wait over I. Sorry about that. Over I. So what's going to happen here now? Well, mu naught n times n is n squared. That's the number of loops in my solenoid, number of coils in my solenoid. Okay. I over I cancel, right? There's the cross-sectional area, there's the length of my solenoid. Okay, so that's what I get. This is the L for a solenoid. Okay, for a long solenoid, right? Okay, so that's this formula. Technically, this is for an infinitely long solenoid, but there we go. Now, what's the point in deriving this? The point in deriving this is to point out something about inductance. As I turn this circuit on, and current starts flowing, the current starts changing, and the circuit starts doing stuff, is this mu value going to change? You're like, no, mu naught is for 4 pi times 10 to the negative 7. That's if I have vacuum in between there. But I probably have like an iron bar or something in there that's got a different mu value. But whatever. The point is that's not changing. That's just a property of the material in the middle of the solenoid. The number of loops in the coil, that's not changing. The length of the solenoid, that's not changing. The cross-sectional area of the solenoid, not changing. In other words, all of these things are constants. L is a constant. And for that solenoid then, none of these depend on what circuit I plug this coil into. I could take this solenoid and hook it into a bunch of different circuits, and its L value stays the same. In other words, I can take that L value and I can stamp it right on the side of the solenoid, because it just depends on the physical properties of the solenoid itself. It doesn't depend on what circuit I hook it up to or anything, right? So that is something to know. My inductance, is something I can stamp right on the side. Now, sorry, I forgot to mention, hey, we said inductance, it's going to be in units of Webers per amp or volt seconds per amp. And I said there's a problem with Webers, and that's not something you measure directly, so it's a weird one to use. And so we talk about volt seconds per amp. That's a little handier, but that's getting long to say, volt seconds per amp. So they gave it a special name. So the unit for inductance, here we go. The units are called, I'm going to symbolize it with a capital H. It's called, believe it or not, a Henry. Okay, so we measure inductance in units of henries, and that'll be stamped on the side of the inductor. We might have its inductance in henries. By the way, plural for henries is henries. I just went right off the edge of the screen, didn't I? Hey, look. See? Henry. Oh my gosh. I hope I wasn't off for much of the video. Okay. There. You copied it down, right? You see the derivation. You can always pause and go not. Okay, sorry if you've been wondering for a while there why I wasn't letting you see the derivation I was doing. It's because I didn't realize I'd gone off the screen. Sorry about that. Okay, so there we go. Hey, there's our inductance. So the point is, this is not a big thing to derive the inductance of a solenoid, I don't think. But it's just recognize that inductance is a property of that material, and it generally isn't changing when you plug into different circuits. It's a property of that device, okay, that electromagnet or whatever loopy thing. Maybe it's a motor, an electric motor you've put in the circuit. It's got a lot of loop, a coil, right? Okay, or something that's got a lot of loops. It's going to make a significant inductance in my circuit. Okay, now, let's talk about what that does. Here is what that does. If I have a nice loopy guy, okay, now, incidentally, inductance, in a circuit diagram, you know how we do the squiggle, wicka, 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 for a resistor, or we do long line, short line for a battery, or two parallel lines for a capacitor, or an A in a circle for an ammeter, or a V in a circle for a voltmeter? Hey, what's the symbol for something that has a lot of inductance? A device with a significant inductance is called an inductor. Just like something has a lot of resistance is called the resistor, right? Or a lot of capacitance is a capacitor. So an inductor, the symbol we use in a circuit is just this. Little loopies. Which reminds us that things like solenoids, right, and coils will have a lot of inductance. That's the symbol. Okay, so good enough. Now, that's the circuit symbol. I'm going to draw this a little bit differently so I can have a perspective picture. Hey, let's say that there is my iron core, right? Let's say that here's the wire, right? And let's say that wire, you know what, I'm going to color code that a little differently so you can see it a little bit clearer. You're like, I can't tell the difference between brown and black on these videos anyway, Mr. C, when the camera's that far off. It's not like in real life, sadly. But there it is. Hey, let's bring that wire around now. Let's say the wire comes around like this. Zoop, 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 zoop. So the current is going to the right in front and to the left behind. When I run the current through then, that would try to make a magnetic field. Field here is really weak. Field in these coils though is going to make a strong field there. In this case, field lines looping around like this, using my right-hand rule for loops, make a strong flux up. This will create a magnetic field shooting out through this guy like this, yeah? So this is my north pole, south pole, my electromagnet. Okay, when I run the current through. So here's what happens. When I first close this switch, I would have an increasing flux up on this diagram, yeah? Which means this will generate then this changing flux through these loops. Changing flux through the loops will make a voltage to fight against it and make a voltage going the other way. So here's my high V, here's my low V. On this guy, he's going to try to push it the other way. So instead of pushing current this way, he's going to try to push, so this will be my high V and my low V, right? This is going to try to push current the other way. Now, here's the question. How big of a voltage will this make, okay? And the answer is, it will push hard enough, and this is the way to think about it, so that you cannot have an instantaneous change in current. It forces the current to build up from where it started. That's the way to think about it. Okay, because we'll do it with other cases where it's already flowing some and then we make a change. So the point is, so in this case we're starting with zero current and then I click the switch. It doesn't just jump up to be the maximum current. If this wasn't here, you would do what for this circuit? You would say, oh, delta V is IR. Well, that's really sloppy. Delta V is IR, Ohm's law, right? And you say delta V, that's the EMF, is IR. And so you'd say, oh, that I would be EMF over R. That's the current in the circuit, right? If this wasn't here, right? The point, and you would think that if you click the switch, it would immediately jump up to be this current, right? This is going to make it have to build up slowly over time. Okay? It's going to force it to start from zero and build up to eventually get to there. That's what it's going to do. All right? That's the effect of having this inductance, this loopiness in the circuit. Is it's going to induce voltage to fight against what's happening here. Okay? How are we doing? Make sense? I think that makes sense. Okay. So it's making a battery trying to push the other way. It acts like a battery. Okay? Now, how big of a voltage is going to make? Enough to balance this out. So at the first instant, it's going to have a voltage equal to the voltage of the battery, actually. It's going to make a EMF to fight against it. Like I said, things that have lots of loopiness, electromagnets, or electric motors, they have the coil where they run current through to get yanked. This EMF that they make that fights against it is called a back EMF. Okay? It's something to consider. Now, you might wonder, Mr. C, I know that there's energy, electric potential energy stored up in the two metals in the battery, right? There's like two different electrodes, right? And electrons, as they move, they're losing energy as they're going through, right? You know what I mean? And so you say, where is this energy going? It's not getting burned off with the resistor here. Where's the energy going? And the answer is, it's going into potential energy stored in the magnetic field. There is energy stored up in a magnetic field, okay? I'm not planning on showing you the derivation in this video, but the energy stored in a magnetic field in an inductor, that potential energy in the inductor, U sub L, okay, is going to be 1/2 Li squared, okay? So you get more energy stored up in it, the more current you have flowing through it, okay? So that is it. So what happens here is some of the energy is going towards building up that magnetic field and storing energy in the inductor when I flip the switch, okay? Eventually, that field will be at full strength, and then the current will be up to its final value, and I'll just have this current of EMF over R flowing through the circuit. And then there's no delta V here anymore. Once that current isn't changing anymore, there's no delta V here. All the delta, there's no induced EMF, and so there'll be constant flux here. And so then just all the voltage is being dumped off at the resistor. Okay, so that's the idea. All right. Good enough. So if I have a circuit, wrapping up the main concept, if I have a circuit that's really loopy, okay, that's going to make that when I run current through, it'll make a strong magnetic field, lots of flux, lots of field lines, then it takes energy to make that magnetic field. And so when I turn on, some of that energy is going to start going towards building up that field. And so not as much current will flow through the rest of the circuit. It makes kind of a back EMF fighting against, it acts like it's making a voltage that fights against the voltage making the current flow. It makes the current have to build up from its starting value. So it can't just jump values, okay? That's the effect that inductance has. People sometimes think of inductance as being kind of like inertia, this like weird magnetic inertia. It like tries to keep the circuit conditions from changing too quickly, right? Okay, it makes it so that things are sluggish. That's the meaning of the Latin meaning of inertia, really, is lazy. It's like this sluggishness in how quickly you can change the current through the circuit, right? Okay, it makes a voltage. The quicker you try to change the current, the IDT, the bigger the voltage you get fighting against it. And L, the more loopy it is, the bigger the back EMF is for that changing current. So yeah, that's the idea. All right. Okay, so I'm going to run through, or should I talk to you about, okay, this was turning on the circuit and building up the current, right? Okay, let's say this has been running for a long time. And then I go to turn the circuit off. And so you say, I take that switch and I go, click. You're like, Mr. C, there's a break in the circuit. That current can't flow. It's going to drop to zero immediately. Bam, no current, right? No. If that happened, if suddenly the current went to zero, suddenly all those magnetic field lines here would go away, right? No current, no magnetic field being made, right? And you see, if there was suddenly going from some current to no current, what's that rate of change? It's an infinite rate of change. You know what I mean? It's infinitely going to zero, immediately, right? It suddenly drops the current, right? That slope would be like negative infinity. Like, that's crazy. That would make a huge EMF to fight against that change, wouldn't it? Yeah, that's what happens, right? And so the point is, if I try to turn the circuit off, right? If I click it off, right? Open the switch, turn it off, then suddenly there'd be less field lines trying to go through here, less magnetic field, less flux. And so what happens is the inductance says, no, we got to fight that change. We got to maintain that magnetic field. And so we're going to try to keep the current flowing that way. And that's what's going to happen. The current doesn't drop to zero immediately. There's still some charge flowing afterwards. Weird, huh? I don't know if you got to see me do the demos where I was making magnetic fields and showing with iron filings magnetic field patterns for different shapes of wire. The device I used to make that high current, that large amount of current flowing, lots of flux, when I turn that device off and I go click, the current doesn't drop to zero immediately. It was like a delay. I don't know if you happened to notice that when I was using that device. But yeah, so the point is, you're like, okay, great, wait. This is what provides the energy per charge. That's voltage, right? Delta V is my delta UE per Q. It provides the energy per charge for them to flow. Like, if I turn this off, it's not getting that delta V. Where is the energy coming from? That energy that was stored in the magnetic field is getting used to keep pumping the current around. Neat, huh? So energy that's stored up in the magnetic field gets used to create an E field to push the charges around. Neat. Okay, that is practically the idea of what happens with inductance, what it does in a circuit. What I want to do now is I want to go through a little bit more of the nitty-gritty of how to think about it for circuit problems now with inductors, okay? So the nitty-gritty of how to think about this, all right? So to do that, I'm going to go ahead and I'm going to project up. This is a page in your packet, all right? And so to do that, I bumped my projector there. So things are not where I want them to be now. But there we go. Okay, do you recognize this page? I know it's hard to see on camera sometimes. If it doesn't focus here where I want, then sometimes it's hard to see. Plus, you know. Yeah, you can see it fine. Okay. Hey, look, here's a circuit. There's an inductor, there's a resistor, there's a switch, and a battery. The battery has an EMF E. This is in your packet. You can see it in the packet, right? This has got an EMF E. This is an inductance L. This is a resistance R. Okay, there's a switch here. Okay? What we're going to do here is we'd love to be able to find the magnetic field strength in the inductor as a function of time, how much current is flowing through this circuit, because it's all in series, the same current everywhere. But the current flowing maybe in the resistor as a function of time. The voltage, the delta V for the inductor is a function of time. The voltage, delta V at the resistor is a function of time. You get it, right? Find all these different circuit quantities as a function of time, right? What we're going to do is we're going to start with calculating I as a function of time. And the rest of these we can kind of figure out from there. Let's do I as a function of time, okay? That's really the main thing here, right? Because we talked about the fact that when I close this switch and turn this on, the current's not going to jump up to its maximum value immediately. So here we go. We're going to run through this derivation. It's going to be a good time. All right, so this is kind of like doing the RC circuit stuff with capacitors in circuits, resistors and capacitors in circuits. If you can think about what's going to happen and figure out what the values are at time 0 and the values are at infinity and kind of sketch out the graph of how it gets there, that's like usually like, 75 to 90% of the points on a problem like this. So here we go. Let's think about what happens at the start. At the start, before I close that switch, how strong of a magnetic field have I got in the inductor? Well, if there's no current flowing through it, there's no magnetic field strength, so that's 0. That's easy, okay? At infinity, right, that B is going to be at its max value, right? So time goes out, and right? You say eventually it's going to be at B max, okay, which, yeah, I mean, if you care, we could put in the equation for the magnetic field at the heart of a solenoid was mu naught. Let's just leave it at B max. Okay, it's at its max value. Okay, which again, if it's a solenoid, we can calculate it. If this was some other shape that's wired in here, then it'd be something different. But this is right now, just do that. Okay, current flowing to the inductor and through the resistor. Well, here, at the first instant, you say we're starting with no current. Remember, the inductor, its job, it's going to make us have to build up from where we are, or if I turn a circuit off, make it have to slowly decrease the current from where I was. It fights against that change in field lines here, which means it tries to keep the current doing what it was doing, makes you have to build from there. So at the start, there is no current. If there's no current, and you say, hang on, we'll come back to this. What's the delta V for the resistor then? Well, there's no current flowing through it, then there's no delta V here, right? Delta V is I times R for a resistor. So that starts off being 0. You say, but wait, if I do the loop law and I go around in a loop, I should end up at the same voltage I started at. So if I'm going up voltage from the low V to the high V, short line to high line, long line here, going through this, I got to go down that same voltage when I get back there. There's no current flowing, so there's no delta V here. The delta V here, it's big enough to completely fight against this and make the current have to build up from 0. That starting voltage for this guy will be EMF going the other way. All right? Does that make sense? The voltage of the battery, canceling out that. It's going to make at the first instant, all the energy is heading towards building up the B field in the inductor. Okay, when I get to infinite time, at infinity, this thing's reached its final magnetic field strength. It doesn't, no energy needs to be being pumped there anymore. You say, I've reached the final current. It's a steady current now, so there's no change in flux through it. And so this will just act like a bare wire at the end. So here's the thing. At the start, this is something to think of. So at the end, there's no voltage across this guy. It's not fighting against it at all, the inductor, right? All the voltage is going to be across the resistor. I'll be going down the voltage of the battery at the resistor, which will be I times R, right? And so the I at the end, because delta V is IR, right? That EMF is IR, yeah, EMF the battery. And so the I will be E over R. That's that maximum current, right? It gets to. So here's the way to think about it. In the first instant, when you first close the switch, this acts like a battery hooked up the other way to fight against the voltage of this guy, right? So in the first instant, it acts like a battery fighting the other way. It's like, in the first instant, it's almost, just for the first instant, it's like a break in the circuit, basically. It pushes hard enough to, no, better not think about that. There might be a battery that fights against that one. So it makes you have to build up from the current you were at, okay? It makes it so you can't jump currents. So the current value has to slowly build up. That's what it does. At the end, it's not fighting against the current at all. So at the end, it acts like a bare wire. This is kind of like, inductor, so this is when we are closing the switch or turning circuit on. The inductor acts, so at t equals 0, inductor acts as a, again, it's almost like a break in the circuit, but that's not the best way of thinking about it, because I could have had it open for a while at one current and then do something else to increase the voltage. And so it's going to pick up from there. It's not going to go from 0 then, 0 current then. But it acts as a, so it's better to think of it as like a battery pushing against the actual battery. So the current has to build up, right? But at time equals infinity, L acts like a bare wire. It's not resisting, it's like a resistanceless wire. So it just acts like a straight wire. Lets the current flow through just fine then. This is kind of the opposite of what capacitors do in a circuit, right? In a circuit with a capacitor, right? Do you remember that it starts off uncharged? When I first turn it on, all the charge is flowing to the capacitor plates and it flows. There's nothing keeping them from flowing to the plates. But as charge builds up, it makes it harder and harder. They repel more charges coming in until eventually the current goes to 0 and the capacitor acts like a break in the circuit. This is kind of like the opposite. At first it fights and stops no current, makes you build up until at the end it acts like a bare wire. With a capacitor, it starts off as a bare wire, it ends up as like a break in the circuit. So it's kind of like the opposite. And that's the way to think about it. Okay, but it's better to think about it, I'll emphasize that enough, okay? That it's making you just have to pick up from where the current value was. You can't just jump currents, that's what it does. Like I said, it's kind of like an inertia, like a inertia for current, instead of an inertia for masses, speeds, velocities. Okay, good enough. Hey, we're good with this. Okay, hey, what do these graphs look like? Well, here's the thing. The size of this voltage that we induce in the inductor has to do with how quickly that flux, so how quickly that B field is changing inside here, right? You say, so at first we're going from no flux to flux, right? You know what I mean? If there's no current flowing and I turn the switch on, suddenly we're getting some flux. That's a huge rate of change, right? So it pushes back big enough to make it start from where it was, in this case 0, right? But then the rate of change, let's say I'm going to get some current trickling, right? And I'll get a little more current and then a little more current, right? And so what's going to happen here is that current will have to build, it started at 0 in this case, so it's going to have to build up from 0, yeah, towards its final value. And that's going to look like this. Now, since the voltage I make is proportional to di dt, right? When I go have a big, quick, if I had a big, quick jump in current, that'd be an infinite slope, and I make an infinite resistance to fight against it, so the current couldn't flow. So it can't jump right up. But the point is then that di dt, I get some current flowing, and then some more, and then some more, and some more. Do you see the slope of this would be di dt? And that slope is getting less and less. And so the voltage that's fighting against me is getting less and less, right? But the point is the time it takes for this thing to finally reach its final current, well, that's going to be an infinite amount of time. This is going to be an asymptotic, okay? Because there's always a rate of change. And the rate of change approaches 0, but as long as there's still a rate of change, there's still a voltage fighting against it. And so you'll never quite get that rate of change to go to 0, okay? It takes an infinite amount of time for this current to reach its full current. The circuit to reach its full current, okay? That's why we talk about infinity. Okay, now if that's my current over time, we just talked about the voltage, the induced EMF. That's what we're talking about here, delta V of the inductor. That's the induced EMF, okay? We said, hey, that's gonna, hey, it's awkward. I want to use an EMF symbol, but EMF is already reserved for the voltage of the battery in this problem. So that's why I had to write delta VL, okay? But this EMF is tend to be the induced EMF, right? Okay, that's what this is. Okay, so the point is we're going to start off with a big voltage fighting against it, but it's going to drop and approach 0 as time heads to infinity. Again, it's going to be asymptotic. All right. What about the delta V in the resistor? Well, I'm going to go down voltage here from the battery. I got to go up voltage here because this fights against it, right? Up voltage. And then I'm going to go down. So the point is, so the point is, these two, I end up back where I started here. These two delta V's have to add up to be that one. And so the point is, at first this is a big voltage, so at first there's no current flowing at the first instance, so there's no delta V across the resistor, right? Delta V is IR for a resistor. And so this starts with a voltage of the resistor of 0. But eventually I start getting current flowing, so I start to have delta V here. I get more and more delta V here, less and less delta V here. And so, right? So this is going to, okay? I don't know why I made that negative. I gotta think about that. Yeah, well, I'm going around, it's fine, just work with it. I'm gonna make that a plus. So the point is, it's gonna be like that. All right, that's just the EMF of the battery. Okay, so that final value I'm gonna approach, it would take an infinite amount of time to get to that full voltage on the resistor. Okay, and then what about the B field in the inductor? You say, well, it starts off at 0, no B field, but it approaches its maximum value as the current approaches its maximum value. Again, for if it was a solenoid, it would be mu naught and I, right? So the bigger the current gets, the bigger the B field I get in the heart of the solenoid. It would eventually reach its final value. When the current gets to max, the current doesn't get to max till infinity. But you get the idea. All right, good enough. Good enough, that's it. Okay. This here is what we're using here, right? That's the delta V is IR for the resistor, right? Okay, and then I rearrange that. That's how I got the current to say it was the delta V over the R would be the current. Yeah. Okay, good enough. About to erase all that, but you get the idea. Okay, so you have an idea of what happens. Okay, the question now is, can we actually now solve for and write an equation and solve for current as a function of time and these other things as a function of time from that? And the answer is, well, yeah. Okay, now you might guess from the whole setup of how I presented this and these grasping these asymptotic things that this is going to be one of those differential equation problems like RC circuits or air resistance problems, and you're right, it is. It's an air resistance problem. It's going to be a differential equation we're going to get out of this because you say how much voltage we get here depends on how quickly the current is changing, but the voltage drop here depends on the current. So some depends on I, some depends on di dt, right? Going on here when I measure my voltage drops around the circuit. So this derivation I have printed out, and I printed in your packet. It's like in my handwriting. Do you want me to talk through it? Well, this video is already super long. I'm going to leave this alone like this. It's a derivation. I think I'll make it in a separate video so you can look at it optionally if you want to see me talk through it if it's not clear. Because there's a kind of a neat trick that I do. There's a couple of things I talk about that I point out. But for now, this is it. Okay, hey, let's go to the other case. Okay, I'm going to do the setup now I'm going to run through for what if I have a circuit and I'm with a current flowing through an inductor and a resistor, and then I suddenly try to turn the circuit off. What's going to happen? Right? We already talked about the fact that there's a magnetic field in the inductor. It's going to try to keep pushing the current. Let's write the equation for current for looking at that situation, though. That's the next page in the packet. Again, if you can talk about the starting and ending conditions and sketch the graphs, you have an idea, you have a place to think about, right? You can start thinking about what's happening here. Okay, so this is now turning circuit off. You'll notice that there's, wait, what? Yes, decreasing current. Okay, we're going to reduce the current in the circuit. So this is me opening the switch, right? Okay. We already know there's a lot of energy stored up in the magnetic field in that inductor. It's the high V side and the low V side. Okay. Some energy stored up here, so when I flip the switch, energy starts getting drained out of here to push the current and keep the current flowing, to fight against the change, to maintain that magnetic flux, to keep the current flowing through. So at the very start, at time 0, I open the switch, turn the circuit off, right? So now, this thing is going to act to try to keep the current flowing. What it's going to do, if it suddenly dropped to 0, if I flip the switch and it really turned off, that would be an infinitely big change in, decrease in current per time, right? Which would make an infinitely big voltage, right? Basically what it's going to do is it's going to make a voltage big enough to make it so the current can't just drop to 0. It's going to make it have to decrease from its starting value. Okay? And so, at the start, it will make a voltage to try to keep the current going. So this was high-low. It's going to be high-low, pushing the current to keep the current flowing around this way. Okay? It's going to keep that current flowing. It's going to act like a battery to keep pushing current through that resistor. All right? So at the start, at time 0, whatever this voltage was of the system, of the delta V that was here before over that resistor, it's going to keep maintaining that delta V to maintain that current in that branch. Okay? So at the first start, voltage of the inductor is going to be that EMF of the battery. Okay, the EMF that it was at, the voltage that this circuit was at here, is going to try to maintain that voltage to maintain that current. That's the way to think about it. It makes it have to pick up from where it left off, okay, when you open the switch. Okay? There is going to be some magnetic field in that inductor. I'm just going to call it B0. Okay? The point is it's starting at what it was originally before someone opened that switch. Okay? At infinite time, it's going to go to 0. Eventually, the current will stop flowing. The current flowing at the start is just the initial current, whatever that was. Which in this case, this circuit, if this had been running for a long time, we could say that was at its maximum value, right? Technically, it takes infinity to get there, but say it was at its maximum. So the voltage here is 0. The B field's at its max strength and everything. It's a nice constant flux through there. And so really, it'd just be, this acts like a bare wire at infinite time. So really, this would just be pushing through a resistor. And so my current, using delta V as IR rearranged, right? And that delta V was just that EMF of the battery originally. So this would just be EMF over R. That's our starting current. And then I turn this thing off. Eventually, the current will die down to be 0. Okay? The full voltage here across the inductor. And so what's the delta V across the resistor? I'm going to go down that EMF, aren't I? Yeah? It's going to go down that voltage. All right? So it's going to go, originally, when this was closed, we had this going up in EMF, act like a bare wire because there was no change in flux going on, and then going down that EMF, it would be I times R, which is why that I is EMF over R. Okay, moving on. However, at infinite time, the current will have died down, and there will be 0 voltage across there, and there'll be 0 voltage across here too. Okay, once I've totally drained all the energy out of that guy, and that magnetic field has died down to nothing, there's no delta V across there anymore. So all these are going to 0 eventually, right? The circuit will turn off completely at the end. Okay, hey, what do these graphs look like? We're starting with the, starting with this one. Sure, voltage across the inductor. At first, there was no delta V across the inductor, right? This was moving, nice steady current flowing through, di dt was 0, and then somebody opens the switch, and it's going to make it a back EMF big enough to keep the current flowing like it was, so it just slowly has to decrease from there. And so we already know that voltage it makes at the start is just that. So this is starting with a voltage to kind of maintain that voltage the battery was providing, and it's going to drop down, approaching 0, right? Asymptotic 0. Okay. Right, what's going to happen with our current? Same thing. We had current originally equal to EMF over R. It's going to drop down asymptotically to 0. Yeah. Okay. What's going to happen with our voltage across the resistor? At first, this was just acting like a bare wire. We were losing all of our energy going through the resistor, right? At the first instant, what this thing does, basically what it does is the inductor acts like a battery to keep the circuit flowing, to keep the current flowing, to maintain that magnetic flux, right? To fight against the change in flux. To make it so the current can't just drop down, it's got to decrease from where it was at. Okay? This is at time 0, at t approaching infinity. Eventually, it's going to be drained, and it's not going to be pushing anymore and have no voltage. It'll just act like a bare wire. It's not resisting or anything. It's like a drained battery, really. It's what it's like. All right, well, kind of. There's no resistance. Okay, so there we go. So that's it. Okay, so the voltage then basically across the resistor, we still have that current flowing, so we still have that delta V of EMF over R, right? EMF over that guy to start with. Am I writing it like going up EMF here and then going down there, and then it should be negative EMF? I don't know. Anyway, the point is, and then it's going to approach 0 as the current dies down to 0. Okay. And in the magnetic field, we started with some magnetic field in the inductor, and as the current slows down, there's going to be less and less current. Because remember that B in a solenoid is mu naught N I. Right? This isn't necessarily a solenoid, but it could be anything else. But it's going to be something proportional to the current. And so it's going to drop to 0 as the current drops to 0. Whatever my starting magnetic field strength was there. You know. Okay, that's it. And this is approaching 0. So that's what happens. All right. Okay, so that's what's happening in these circuits. Because every circuit is a complete loop, every circuit technically makes a magnetic field through a loop, and so it has some inductance. But really, the inductance isn't big enough to worry about unless you have something really loopy, an inductor in your circuit. Okay? And so then we only worry about it. All right. Hey, that's the main gist of what's going on. If you understand this, you can think about where circuits are coming from and where they're going to, right? And you can logic through what the values should be at different points in time, okay? At the start and at the end, at least. You can logic through what it should be like, and you can think about like how it's going to get there, and that's good stuff. The actual calculation for I as a function of time, if I have I as a function of time, I can plug in there and get B as a function of time, or so on. I'll put in another video if you really want to see it. Email me, let me know, and I can share that with you. Otherwise, I've got written out the derivation. You know what, let me for sure put another video. Okay, I'm gonna go ahead and stop this one here. But yeah, that was good stuff. Yeah, You got a lot of information here. I'll just say this, just so you know, the way that we're going to approach these problems is we're going to use Kirchhoff's loop law for the circuit. So we're going to do our delta V loop is 0 going around the circuit. And so you say, hey, as I do that, then like if I was charging, I'd go up the voltage of the battery. If I was like turning the circuit on, I go up the voltage here and then go down my induced EMF and then down IR for this and be back equals 0. If I don't have the battery, I'm just linking across here and just kind of turning the circuit off, then I'm just going to say, going around in a loop, I go, you know, up the volt EMF of this guy and then down the EMF of this guy, down IR. So up L di dt. Well, for this turning off case, it looks like this, because that's how you write the voltage for an inductor, isn't it? Right? Okay, this is the way you put it into Kirchhoff's loop law, negative L di dt. And then I go down IR. This derivation I didn't put in the packet for discharge, for turning a circuit off. Okay, that's what the starting line looks like. Okay, this derivation is actually way easier. The one for turning the circuit on is more complicated, and that's the one I wrote out for you. This one, actually, the math is really easy. I'll whip through this math real quick on this one. Like the other one, you have to do like the substitution, and it's crazy. But here, take a look at this. Hey, I'm trying to, now, what I want to point out to you is like, wait a minute, negative and negative equals 0. How's that working? What's this? This is for turning the circuit off. So what's di dt? My rate of change of current, my current is decreasing. This is negative. And that negative makes this term positive. So then positive and negative give me 0. Okay, so in case you're wondering, that's what's going on there. I just want I as a function of time. I'm just going to, I have I and di dt. It's a differential equation. I got a variable and its derivative. I just want to solve by separation of variables, get the i's and di's on one side, the t's and dt's on the other side, and integrate. So moving this over, I like to get my variable by itself. Remember? I don't know if you remember with the coefficient of 1. Let me move this to the other side. Or just move the IR to the other side. It'll look like this. IR is negative L di dt, right? Okay. Now I'm going to go ahead and divide by R. Okay. Now, what I'm going to do is I'm going to treat this like one chunk. I'm going to move it here. It's going to be going back and forth. Sorry about this. I'm going to move the R over L to the other side. I'm going to move the dt to this side. It looks like I'm multiplying, but you know, what are you going to do? But that's it. So I've separated my variables. I've got my i's and di's on one side, t's, I don't really have any t's, but dt's on the other side. Now I integrate. In this case, if I had the circuit running and I'm just turning it off, right? Okay. Oftentimes they'll do something where they'll have like a circuit like this. And they'll say, hey, we're going to simultaneously, don't ask how, close this switch and open this one. So I open this one that takes the battery out of the circuit, and closing this one then lets this discharge around. But anyway, point is, we're going to go from the original current to current at some point in time. At infinity, that current would be 0 to turn the circuit off. But I want to find I at any time, so we're going to go from time 0 to any future time t. And so initial current to any future, which the initial current is just EMF over R. Okay, so this is discharging again that we're doing. Or sorry, discharging, turning the circuit off. Okay, this was a lot easier to set up and separate the variables. That's why I didn't write this one out. So at this point, the math should be fine from here. R and L are constants, right? You can stamp it right on the side of the resistor. Resistance is this many ohms. You can stamp right inside the side of the inductor. That's a constant, doesn't change with the circuit. My inductance is this many henries. And so constant, just integral constant times dt, that's just t. This would be negative R over L t minus R over L times 0, so it's just negative R over L times t. On the other side, this is just going to be natural log of I. It would be natural log of I minus natural log of I naught, or natural log of I over I naught, using that property of logarithms. Yeah, you have some value. Okay, let's unlogify this. E to this power equals this. So e to the negative R over L times t is equal to I over I naught. Move the I naught to the other side. We are almost done. where it says I naught, I'm going to put in the values they gave me in the problem. That I naught is E over F over R. That original voltage of the battery over R. So my I E to the negative R over L times T. Okay? And you say, hey, this exponential here, right? As time goes from 0 to infinity, e to the 0 would be 1, and as it goes to infinity, e to the negative infinity would be 0. So this value goes from 1 to 0. Well, this is just 1 to 0. 1 times I naught. Just I naught is the value at time 0, and goes to 0 and infinity. That, in fact, is what this graph is doing. Okay, starting at that initial value EMF over R and going to infinity. Okay, perfect. So this is like the percentage that you're at. Hey, this circuit then, I can imagine having circuits that would drop more steeply than this one or drop more shallowly. All of them will take an infinite amount of time to drain, to totally drain the energy in that inductor. You say, but I can talk about how quickly they're dropping. How do I compare that with a time constant, tau? What's tau? It's the value for t that simplifies that exponent, makes that exponent -1. That exponent, again, negative r over L times t. I don't know if that was any clearer. What value would t have to be? T would have to be L over R. That would make this -1. That's the time constant for what we call an RL circuit, an inductor and resistor circuit, inductance and resistance circuit. That's the value that makes that exponent simple. That would be what? When the current has dropped to be, what's 1 minus 0.632? 0.368. That'll be time when I is 0.368 or 36.8% of I naught, its original value. Okay, that's the time constant we talk about. Remember that's 1 over E. That's 1 over E. This becomes e to the -1, 1 over e times that, right? 0.638. Okay, good enough, right? If I was turning the circuit on, if we did that derivation, you'll get that same time constant. That'll be the time to get to 63.2% of the maximum current in the circuit. Because that'll be 1 minus e to the -1 when you're at time constant. Okay, that's it. Hey, like I said, this was the easy derivation. The other one I've got written down on paper for you. You probably will, I could almost guarantee that you won't have to do this derivation. But understanding what's happening in the circuit and why, and like figuring out like what the final value should be and the initial value should be, like I said, this is gonna be the bulk of it, I would think, and being able to sketch the graphs. Okay, hey, that's it. I'm cutting it off here. That's it. That was way longer than I meant this video to be. Hey, good luck with working problems here with inductance, okay, in circuits. All right, and this is like the last official, I think, topic that's on the AP exam. There's more stuff that I'd like to talk about implications of this, but I usually talk about those after the AP exam. All right.